Hello guys, welcome to the new video. In this video and in the next coming videos, we'll see about the stability factor of various biasing techniques in bipolar junction transistor. So in this video what we'll do is we'll see what is stability and why we should study stability, what is stability factor S, and also at the end of the video we'll calculate the stability factor of fixed bias circuit. It is one of the biasing techniques of bipolar junction transistor. So what is stability? Stability means the state of being stable, that is to be robust. I always felt that building a circuit is similar to building a house. We need to make sure that our house is robust, that is it is resilient against the variations in rain, wind and other environmental factors. In the same way, when you build a circuit, you need to make sure that it operates properly across all temperatures. That is, suppose say you built a circuit at say 30 degrees Celsius and it works very well, but you need to consider other factors such as temperature, pressure, which may vary according to the environment. If you take your circuit to some cold place, it should work in the way that it worked at 30 degrees Celsius. That is the proper design. Okay, that's how you need to design a circuit. As you can see, if there is heavy rain, this roof may fall. Then that is not a proper design of this house. So it is important for us to study stability in BJT biasing circuits. What is a bipolar junction transistor? Uh, we learnt about that in the previous video, and there are also some biasing circuits, biasing techniques, like there is self bias or fixed bias circuit, then there is collector to base bias, and then there is voltage bias circuit. So we need to study all these circuits and we need to study their stability, that is how strong they are with the variations in temperature, pressure, etc. Okay, so we'll look into that. So that's all I wanted to say in with this example. Now what we'll do, we'll take a fixed bias circuit. So before that, we need to understand another thing called as stability factor. Stability factor is denoted by S. So this is nothing but in terms of BJT I'll explain, but first understand, let's understand in terms of common terms what is stability factor. Suppose say this is our house and this is a rain. Okay, so stability factor is defined as, say this is the roof. If heavy rains will occur in this region, this roof may just shift a bit. Okay, so let's define this house roof as HR. Okay, in that case stability factor is defined as delta of HR, that is roof, change in this position of roof with respect to this rain. Okay, so you do not want this value to be large. It means for greater change in rain, this roof may move, that is it may shift to its right. Okay, so it may shift here. This is delta HR with respect to change in rain. Okay, we do not want that to happen, so our design should take care that this value is as small as possible. So that is what is a stability factor. So we'll use this terms in terms of actual circuit. If we study the fixed bias circuit, we'll find the stability factor and all that. Okay, so this is the fixed bias circuit. It is also called as base bias. Okay, so these are the, we'll apply KVL to this circuit, then we'll get VCC is equal to IB into RB plus VBE, and also VCC is equal to apply KVL here. We'll get ICRC plus this is VCE, collector to emitter voltage. So as we all know that BJT is mainly used as an amplifier. So in order to work it as an amplifier, what we need to do, this is the output characteristics. Okay, this is IC, that is collector current, and this is VCE. So in order to use this BJT as an amplifier, we need to fix a operating point. Okay, this operating point we fix in such a way that it is here. It is not in the cutoff region, it is in the active region. This is the active, forward active region. Okay, this operating point is called as Q, and its coordinates are this is you can use this IC and VCE. So this, whenever we are designing any analog circuit, that is say BJT, we need to make sure that this operating point Q is stable. That is, it stays at this point no matter what. But however, there are some device parameters of BJT. They are reverse saturation current ICO and base to emitter voltage VBE and beta of a transistor. So these three vary with respect to temperature, that is outside temperature. So we need to make sure that this operating point remains at this position irrespective of the change in temperature, that is say minus 50 degree or plus 150 degree. No matter what, our operating point should be here. But however, that's not the case with all circuits. Okay, say we are dealing with the biasing circuits, right? Biasing techniques. So this is fixed bias. It may not be possible for us to fix this operating point here at say 100 degrees Celsius, even if you take care of all that. So it is very important for us to calculate the stability of the circuit. So if we compare stability factor of 3 or more biasing techniques such as fixed bias, collector to base bias and voltage divider bias, we'll get to know which is the best technique of biasing a BJT. That is, so that's how we'll see now. So in this video what we'll do is we'll calculate stability factor S. So as I said earlier, stability factor is means, see, IC is one of the parameter, that is collector current. We want collector current once designed to stay at that value irrespective of change in temperature. However, it may not be possible with fixed bias. So let's calculate the stability factor, that is how much our collector current varies, that is denoted by delta IC, with respect to change in ICO. So this ICO is called as reverse saturation current. So you can watch my previous video about reverse saturation current. I have given a detailed explanation about this. So this reverse saturation current is due to minority carriers, that is all blah blah stuff. So it varies with temperature, that is it increases with increase in temperature. So if this increases, our IC will also change. So how much, by what amount it will change is denoted by the stability factor S. So we are gonna calculate this value and this of this for this circuit. Okay, so let's use the equations now. So we all know that the collector current in this technique or anyway in BJT is beta times IB. However, there is a small role played by the reverse saturation current. So the total collector current, actual collector current is equal to beta times IB plus beta plus 1 ICO. So what we want is we need to find delta IC upon ICO. So what to do in that case? We'll differentiate this equation 3 with respect to ICO. So what will be delta IC upon delta ICO? This is nothing but yes. Okay, it will be beta times delta IB upon delta ICO plus beta plus 1. Okay, this will be 1. So we have done this. This is nothing but S. Okay. Now what we need to do? We need to find delta IB upon delta ICO. So to do that, we need to differentiate equation 1. Okay, with respect to delta ICO. So let me take another page. So we'll differentiate this equation with respect to delta ICO. Since VCC is constant, the differentiation of VCC with respect to ICO is 0. In the same way, RB is constant. So this will be delta IB upon delta ICO. And again, since VB is constant, the differentiation of this VBE with respect to ICO is 0. Okay. So we are left with this equation, delta IB upon delta ICO into RB is equal to 0. Since we know that RB is constant, we get delta IB upon delta ICO is equal to 0. So substituting this value in this equation, the equation 4, we get the stability factor S, that is delta IC upon ICO is equal to beta plus 1, because this factor is 0. So this is the stability factor of fixed bias circuit. Okay, so for fixed bias, this is the stability factor. Since we know that beta will be very large, say around 200 or something, this value is extremely large for a fixed bias circuit. So the conclusion is that fixed bias circuit is not stable and the operating point will not stay at that point. Okay, so this is our operating point. This will not stay stable according to the change in temperature. If temperature changes, this ICO will change, and hence our operating point may move. It may move here, here, here. It may move to cutoff, and your amplifier may not work as an amplifier. So designing this, finding out the stability factor for any biasing techniques is must for every analog circuit designer. So this is the stability factor for fixed bias. We'll find out the stability factor for another two biasing techniques called collector to base bias and voltage divider bias. Okay. Till then, if you have any doubts, please use the comment section. Thanks for watching, and please don't forget to subscribe.